So looking at the Nernst equation, the equations on the new AP test, this is really all you have. We have delta G naught, delta G under standard conditions equal to negative NFE, standard cell potential. And we have this, right? If delta G is 0, or if the potential is 0, then we say it's at equilibrium. Nothing's moving, right? Energy's not going one way, not going another. So we have 0 potential. The electrons have stopped. If that's the case, then you can solve for K. First, let's derive the Nernst equation from what we have here. So if delta G is 0, then we don't need to worry about it, and we have this. If all we do is kind of move this to the other side, then we get this. We get a case which is not at equilibrium. And if it's not at equilibrium, we should be writing Q and not K. So we have this equation, and now we substitute in, right? We have delta G naught equals negative NFE naught, and we plug that in. For delta G, we don't put the naught. It's not the standard conditions anymore. It's not 1 molar, it's not 1 ATM. Probably we're still dealing with 25 degrees Celsius. We have this. Substitute that, and nothing changed here. Then divide the whole thing by negative NF, the number of moles, and Faraday's constant. So that Faraday's constant will appear on your formula sheet, and N, just the number of electrons transferred in the reaction. So we end up, the negative NF cancels out here, this becomes negative, and we get negative RT over NF ln Q. If you are dealing with log, then we have this constant that just kind of makes these two things equal. So either one of these works. Sometimes you see, you'll see books or something solving it with log, a lot of times with ln as well. So if we want to solve for K, we would say, okay, then there's no potential. So that's 0. Now we move this to the other side, make it K, and then we can figure out what the equilibrium constant is equal to for a reaction. I don't know, so that's Nernst. I don't solve, just do the math.